There it is. Okay. So this class starts in chapter 1 of your book, which you will now have access to through the course content, Pearson eText link. You can buy a paperback version of the textbook. I don't recommend it since you've already paid for it, but if you want it, you can get it from the bookstore. In addition to me giving the lectures, in the lecture slide portion of the Blackboard, there will be all of the lecture slideshows that I give. So you have 3 ways to get the information. Me talking about it, there's going to be a video of it, and there's a slideshow. Also, it follows directly along with the textbook, so you got it. You can get it. But let's talk about a modern view of the universe, because it's always good to know where we're starting if we're going to be going somewhere else. So first, I want to start asking the question, where are we? What is my place in the universe? And when I say what is my place in the universe, I don't mean spiritually, right? That's not a metaphorical question. I mean literally, physically, where am I in the universe, if that's even a question that has meaning. So we're going to start here. We're somewhere on this thing, right? In a state called Kentucky. All right, y'all. That state is in a country called the United States of America, which makes up a continent about y'all called North America. Now, all of that is on a planet, a big oblate spheroid called Earth. If anyone wants to talk to me about flat Earth, please see me at any point. I'm ready for you. But we're going to keep zooming out, right? We're going to assume that we can zoom out further and further until eventually we are above the plane of the solar system. Puts us about there. Now, BT dubs, that is not the scale, right? I just want you to be able to see the different planets in the solar system. But then I'm going to zoom out even further, whoop, so that we can see the entire Milky Way galaxy. The galaxy that we live in is named the Milky Way galaxy. We're about right, y'all. In the Sagittarius arm, well, the Orion spur of the Sagittarius arm of the Milky Way galaxy. But I'm not even done yet. I'm going to zoom out even further, so far that you can see not only the entire galaxy, but our buddy galaxies as well. This is Andromeda. That's about 2.5 light years away. That's the Triangle Galaxy, and that one's name I don't remember. And then zoom out further. You get the point, right? I keep zooming out, and there's always more and more and more stuff to look at. Now, at some point, I zoom out far enough so that I'm at the scale of the entire observable universe. Of course, this isn't something you can literally accomplish, but for this little show I'm doing here, let's just say you can zoom out far enough to be able to view the entire observable universe. You can see that there's organization to galaxies along with voids in between them. The point is, there's some pretty big numbers and some big spaces and big stuff happening here. That is the whole point. You know, I got a video about it. Y'all don't know yet. I have videos for everything. Let's do it.
Nothing can travel faster than the speed of light. It moves through space at 300 million meters per second. Astronomers use light years to measure the enormous distances in space. Using meters or even kilometers just isn't practical. Although light travels very quickly, distances in space are vast. It takes 8.3 minutes for light to travel from the sun to the Earth. This means we don't see things as they happen. A sudden change in the sun's brightness would take 8.3 minutes to be visible on Earth. Our nearest star after the sun is Proxima Centauri, which is 4.2 light years away. When we see it at night, the light we see actually left the star 4.2 years ago. Despite the speed of light, the vast scale of our solar system means that when we look into space, we're actually looking back in time.
Awesome. That's a pretty cool statement. When you're looking into the distance in space, you're actually looking back in time. And that's because light does take some time to travel. Now, we're going to get into that quite a bit over the next few days. But I wrote up on the board, and I'll write in a better place. I wrote the speed of light, and I'm going to write this millions of times up here. But I just wanted you to see this really quickly. I always put the comma in the wrong place. There you go, 300 million meters per second. So that's fast, right? A very fast speed. And like I said, we'll talk more about that later. I just wanted to put it on the board so that we could all look at it and be like, ooh, that's hot. But since we're going to be dealing with some distances, let's start getting a sense of distances. So what does that even mean? Okay, well first, a meter is a little more than a yard. I think most people know that, but if you don't, here's a meter. Here's a meter right here. It's 100 centimeters. So 40 some inches. And this says that a person is about 2 meters tall. Now, this is a pretty tall person, maybe like 6'5", is about 2 meters tall. But that's not an unbelievable height for a person to be. Sure, right? Okay, so we're still dealing with some pretty decent distances, nothing crazy. And then I'm going to make my first jump. And I want to introduce to you a unit called an astronomical unit. An astronomical unit is a commonly used unit within the range of the solar system. Here's the information you need to know about it. An astronomical unit, written as an AU, is the average distance from the Earth to the Sun. Here, right? An astronomical unit is the average distance from the Earth to the Sun. Now, that doesn't really give you much scaling, because you're just like, okay, cool. But in order to scale it to something you're more familiar with, that distance is 150 million kilometers. And that's a number you'll need to utilize quite often. $150 million kilometers. Now, before I write the unit of kilometers up there, let's take a small step back. This is a meter, right? You know that? What's a kilometer or kilometer? Well, a kilometer is 1,000 of these. It takes 1,000 of these to make a kilometer or kilometer. So, 150 million thousands of these things. 1,000,000 of these. So most often you'll see an astronomical unit $150 million kilometers. But you could also write it as, and the only reason I'm doing this is just to show how ridiculously large the number is. 150, we're not done, billion meters. right? So if it takes 150 million kilometers, then it takes 150 billion of these themselves. So that's a lot, right? Are we getting? We're understanding. These are some large distances. So what this means is that every person on the Earth, well, minus a few, we'll just take an average of 7 billion folks. We have them stand end to end. You make about 10% of the way there. Now, this doesn't seem like a very large amount. Wow, only 10%. But the fact that there are enough people on Earth in order to make it 10% by standing on each other's heads is kind of amazing in itself. But the point is, it's a very far distance. So we're going to be working with some super large distances. Allow me to repeat. The important things for you to remember on this page is what an astronomical unit is, what the distance means, and what it's equal to. Those are your important things. Questions so far? Yay. Okay. Now I have written on the board the speed of light, but you'll notice something. The speed of light is written differently than what I had, right? I had it written in a different unit. I had it in meters per second, which made it more. You will often see the speed of light written 2.99 times 10 to the 5th kilometers per second. I've seen some super lazy people just write 3 times 10 to the 5th kilometers per second. And yes, this is an approximation as well, but I feel like it's a better approximation than that one. Regardless to which way you write it, that's a really far distance. Anybody have to drive to school today? Anybody? Yes, sir. How far do you have to drive?
Probably about 6 miles.
Drove about 6 miles? Okay. That is approximately, this isn't going to be right. We're going to say that's about 10 kilometers, right? So he drove about 10 kilometers to school this morning. What's your average velocity, sir? Average speed? About 60 miles per hour. That's going to, this isn't going to be right. We're going to say that's 100 kilometers per hour. All right, so I'm going to put his speed up here. 100 kilometers per hour. This is a much larger distance, right? This is about 3,000 times larger, and the time is much shorter, so 3,600 times less time. The point is, this velocity is faster than any speed that you will ever imagine going. In fact, it's the speed limit of the universe. We'll talk more about that later. But this 299,792 kilometers per second is very fast. And even though it is very fast, it is still a velocity, meaning that things have to travel that distance. Now, for me learning astronomy, that was one of the more interesting concepts to understand, that things, everything, including light, must travel a distance. So now, when I hear the statement, when you're looking into the distance, you're looking back in time, I think, oh, I understand. The light appeared at a source, and then it had to travel to me. So the light that I'm seeing is the light that was created when it left the source. And then it must get to my face. Here's another way of thinking about it. when you look at something far away, you are not looking into the distance. The light that you are seeing is the light that has reached your face. If it doesn't reach your face, you can't see it, right? You can't observe light that doesn't exist to you. So the light has reached you. The light has traveled the entire distance. And so it has, I don't want to say aged, so it was created when it left. Here's a direct example. I'll use the sun. It takes light approximately 8.3 minutes to reach us from the sun. So if the sun just magically disappeared right now, we wouldn't know for 8.3 minutes. Because, it would still look like it was there. And then 8.3 minutes later, it just be disappeared. Pretty interesting, right? Well, I think it's interesting. I also want to show you all that there is some math that we can do with this. And like I always say in my lectures, yes, astronomy is pretty pictures, but there is a physics underpinning that supports all of these pretty pictures. And so I want to do some math to help you all see that. So I want to let everybody get all the notes that they need to. And I'm going to ask you all some questions. Okay. So if you hear someone say the speed that they went, 50 miles per hour, or however fast, you'll notice that is miles per hour. Another way you can think of that is it's a distance divided by a time. Or it could be written x over t. So a speed is a distance over a time. Awesome. We know the speed of light. Can someone please remind me what the speed of light is?
299,792 millimeters per second.
Yes, thank you very much, ma'am. I appreciate that. 299,792 kilometers per second. Please be aware, folks, there are some things that you're going to want to have in your heart, your head, or your notes. This is one of those. It needs to be like, I can just say it, right, at any point. I usually just say 2.99 times 10 to the fifth, but it doesn't matter, as long as you have access to it. Okay. So we have this velocity. We're going to do something with it. In fact, I want to verify the amount of time it takes for light to get from the sun. I want to see if I can verify the amount of time it takes for light to get to the sun. But in order for me to do that, I need to know the average distance from the Earth to the sun. Can anyone remind me of the average distance from the Earth to the sun? That is true. But I don't want to assume that. Yes, I know it's true, but I want to calculate that. What about in kilometers? 150 million. Thank you all very much. I'm going to write all of these letters. I don't see numbers here. Awesome. So now I have a speed or velocity, and I have a distance. Since I know that distance over time equals velocity or equals speed, I should be able to find out how long it's going to take for the light to go from the sun to the earth. And again, this is just me verifying, right? I see all these numbers up here, and I'm like, sure, they're true, but I want to use my own math to be able to check that. This is not something that you necessarily, specifically need to know how to do. However, the concepts behind this will return in your homework. So watch my steps. This, I'll write it again in a different color, larger. This says that velocity is equal to distance over time. This says that given two of those objects, I should be able to find the third, or sorry, given two of those qualities, I should be able to find the third one. So let's test it out. Let's test it out. I'm going to use the distance from here to the sun, or an astronomical unit, as my distance. And if you don't mind, I'm going to shorthand that a little bit. Questions on why I wrote it like that? 150 million times 10 to the power of 6. Divided by the time, which we don't know. But we do know it's equal to the speed of light, because that's a velocity. So I'm going to shorthand here. Well, look at that. I can solve for the time, right? Yeah, we can. If I start moving too quickly for you, please let me know. I tend to just roll through this part. And of course, if you ever have a question about something but you don't want to ask it in class, send me an email afterwards. Just make sure I answer your question. We're going to reorganize this so that we can solve for the t. I'll divide both sides by 2.99 times 10 to the 5th. And that should tell me the time. If my math is even halfway decent, this should tell me the time. I'll give you all a second to write this down, and I want to talk a little bit about how to enter this into a calculator. Hopefully everyone has either a TI-30X2S or an 80 series TI calculator, because those are the easiest to use. To enter a number such as this, you'll press 150. I know you can't see it, but it just says 150. In the upper left-hand corner, you have a key that's different than the other key or different color that says second on it. If you're using an 80 series, it's underneath all the graphing function. If you have a 30 XQS, it's right there. Mine's yellow. You'll press that. That's your second or shift key. After pressing your shift key, you can just press the double E key, which is the key right above your 7. And then 6. And then you'll notice your calculator says exactly that. The good thing about the TI calculators is that they understand that this is one number. So you don't have to put any parentheses around it or quotation marks or anything. Your calculator's like, oh, that's a value. Cool, I got it.
What's the last button?
6. It's in here. So let me write it up here. That's at the upper left. The double E is right above your 7. And that gives you this value here. If you have a calculator and you've been like taking furious notes, take a second to pull it out and check it out and make sure you can find all of those. Now, if you're using some other calculation device, it can still be done. I'm just not sure where all your buttons are. However, the good thing about the TIs is they understand that all of this is one number. Can you just press 150000000? Sure, you could, but you ain't got it. You can just press that. So I want to give everyone a second to use all of their calculator skills to come up with a value. Whatever it is, right or wrong, let's get one. All right, I think I saw everybody put their pencil down. Oh, nope. Okay, so I got a time. And you might look at this number and think, goodness gracious, what does this even mean? When I look at 501.67, I may think, what? But you've got to think of the units. Since your velocity or speed is in kilometers per second, this is also in seconds. 501.7 seconds. I'll give everyone a second to check either, yay, I did a good job, or hey, I should fix this for next time. But Mr. Palmer, 501 seconds, I mean, gosh, I don't usually count things in seconds, so how long is that? Well, I would rather have it in minutes. I think that'd be more helpful to have this in minutes. But first I need to know how many minutes are in, or how many seconds make up a minute. Can someone tell me? Yes, there are 60 seconds in a minute. So I'm going to divide this by 60. And I bet now you'll get a number that seems like something you've heard before. $8.36. Yay. That's very close to the 8 light minutes, or the 8 minutes that was posted on the other page that said light takes 8 minutes. Well, to be more accurate, it takes about 8.36 minutes, but close enough, right? There were some approximations used. That's an approximation. That's an approximation. So this number is not exact. But it's still pretty awesome. And it introduces a concept that I want us to all be aware of. Please notice that because the speed of light in a vacuum is constant, the speed of light in a vacuum is constant. Because of that, you can accurately measure the distance of something based on how long it would take light to travel that distance. And I think you all have heard of this before, such as a light year, right? And I think I have a whole section of this lecture on it, so I don't want to jump the gun too much. But I do want to go ahead and make sure and say, please be aware, everyone. Hello in the camera. Also be aware. Light years are not time. A light year is a distance. All right, is it all right if I clear this page off here?
Yeah.
Okay. Anybody? Just want to make sure. Everyone on the camera, a light year is a distance. Please do not measure time in light years because that doesn't make any sense. And like I said, I know I have a section later in the lecture on light years, but goodness gracious, this is important enough for me to just get it out there right now. Okay. Let's continue. I'm also going to open my textbook here, just in case I run across something super interesting I want to talk about. There we go. Okay. Because the speed of light is constant and it takes it a while to travel, we can measure the distances away from objects based on how long it takes light to travel. So if you see a distance such as 8 light minutes, that means that it takes light traveling at this velocity 8 minutes to travel that distance. If I see the distance of 1.29 light seconds, that means that light traveling at its constant speed takes 1.29 seconds to travel that distance. So yes, light seconds and seconds are related, but they're not the same unit. They don't have the same meaning. Oh, and BT dubs, guys, in order, the distance between Earth and the second closest star, with the first being the sun, is going to be 4.3 light years. It's real far. We'll calculate that distance at some point, but it's far. So we got some huge distances going on here. And as humans, we have a hard time comprehending giant or infinitesimally small things. So we're just going to use math a whole bunch to try to comprehend it better. Like, I asked my son the other day, I was like, can you imagine being 70 years old? He's like, yeah. Like, can you imagine being 150? He said, sure. Like, what about 1,000? He's like, sure. I'm like, what about being 1,000,000 years old? He's like, I'm like, yeah. What would you do if you were 1,000,000? He's like, I was like, yeah. As humans, you have a hard time comprehending giant things. So we're gonna use a lot of math to understand this. And also, if I get too excited, just make sure and be like, whoa, calm down. Because when I talk about astronomy, I'm just like, whoa, it's so cool. If you don't feel like writing all this down, please don't. Please remember, you can just pull up this slideshow. It will be on Blackboard in the lecture slides section. And if you could like print them out or whatnot. Let's move on a bit. Oh, this was my page for calculating distances. I forgot I had a page for that. Okay. As we work with the System International units, the metric systems, metric system, I wanted to make sure that we had a list of all of the metric prefixes. So you can, of course, like I said, print this off if you want, or bring it with you, put it on your laptop. Because we'll often use a unit and then use a metric prefix. For instance, when we were talking about meters, and then we said that a kilometer is 1,000 meters. Well, you can see here on this list, okay, the kilo equals times 10 to the third, which is 1,000. So a meter is this one, but a kilometer is this one times that value, so times 1,000. So we just use the metric prefixes to change the sizes of things. Definitely, I wouldn't recommend writing down this whole list. At most, just glance at the ones that you think you might need most often. Centa, milli, micro, nano, mega, giga. I've seen femto, people use that a lot. But most of them you don't really need to know. Kilo, centa, milli, nano. They're the most common used ones. And the reason why is because in astronomy, you use kilometers, that's not enough. You use astronomical units, that's not enough. Even if you use this many, it wouldn't be enough. So we just change bases. But I wanted to make sure that you have that handy if you needed it. talk more about this later. Okay, so that's a super cool video for multiple reasons. Video number one is, I remember the first scale model of the solar system I ever found online. It was to scale, all the planet sizes and distances were to scale, and it was the same scale. And I just remember how long I had to scroll down because it was like vertically oriented. How long I had to scroll down from Neptune to reach Pluto. Like, it wasn't 30 minutes, but it was a long time of me just like scrolling. And every once in a while, a message would pop up that said, hey, keep going, keep scrolling. You're 1/5 of the way there, you're halfway there. So it's really hard to get a model that has the same scaling for both size and distance because the distances between the planets are huge. Okay, so here's a question really quickly. Let's think about it. Which would take the longest for a radio signal to reach from Earth? Now, as we read this question, we have the obvious thing it's asking us, but we need to think a little bit more about what it's really asking us. What it's really asking us is, which is further away from the Earth? But because, of course, a radio signal, which is light, is going to travel at the speed of light and will, of course, reach whatever's closest first. So, the moon is right next to Earth. So not that one. All right, next we have Mars, Jupiter, and the Sun. Well, let's go backwards. Let's go backwards. Here's the Earth. Let's just say Mars is right there. Jupiter's all the way over here. The Sun's down there. So, since of all these four things, Jupiter is the furthest one away from us, it's going to take the radio signal the longest to reach Jupiter from Earth. Not that Jupiter is the furthest thing away from Earth of like everything ever. It's just of the objects in this list, Jupiter is the furthest. The moon's right next to us. Mars is at least 0.5 astronomical units away. The Sun is about 1 astronomical unit away. And Jupiter is at least 4 astronomical units away. And maybe even 5, depending on what side of the Sun it's on. Or maybe even 9, sorry about that. Okay, we're still talking about distances, right? Because this is important. It's important to get an idea of the scaling. The Voyager probes are the furthest things away from Earth right now. I have heard or read some articles that say that New Horizons may overtake them eventually because New Horizons is moving faster. But as of now, the Voyager probes are the furthest things up. They're both launched in 1977, and believe it or not, we are still receiving information from one of them. And I think they record it on 8-track tapes. You probably don't know what those are, but so before their MP3, there were CDs. Before CDs, there were cassette tapes. Before cassette tapes, there were 8-track tapes. And I think the information is recorded on those, because that's right around that time. Hilarious. This is just a broad image of what the Voyager probes look like. They both look pretty much the same here. We got an antenna. We've got star trackers, things to help it focus the right direction. I think it's Voyager 2 that's still sending information back. And it's running super low on energy, of course. So it's like, hey, I can do 2 things right now. I can keep myself facing Earth and send back radio signals, but that's all I can do. I like Star Trek, so there's a picture of the Star Trek Voyager. Anyway, okay. Now we want to go back to the idea of a light year. We mentioned this before, but now I want to start hitting it a little harder. But before I hit it too hard, let's talk about something. Okay, so as stated, we live in the Milky Way galaxy, and I want to say that there are about, I'm trying to get a nice number of the number of stars in here. Well, we'll just say that the diameter of it is 100,000 light years in diameter. So that's pretty big, right? And the next nearest large galaxy to us is the Andromeda Galaxy. That's about 2.5 million light years away over there. So with such huge distances between everything we talk about, it's got to take a lot of time for that light to get here. For instance, the light from the Andromeda Galaxy, which is 2.5 million light years away, must have taken 2.5 million years to reach us. And of course, the further away things must have taken further. But this also tells us that based on the age of the universe, there's only going to be a certain amount of universe that we're able to see. And we call the amount of universe that we can observe here's the kicker, observable universe. So the amount of the universe that's within range for us to experience, we call the observable universe. Is there more universe? Maybe. We can't observe it, and we never will be able to. It might be that the observable universe is here, and the entire universe is here, and we can only see this amount, but we're never going to know that because this is all that we can observe, right? So the observable universe is the portion of the universe that can be observed, either directly or indirectly. For instance, can we see dark energy? No. Can we observe its influence? Yes. Therefore, we can observe it. So I just wanted to really quickly introduce the idea of the observable universe and the idea that there could be more. But we don't necessarily know that. I also want to introduce the idea of the Big Bang, but I want to do it in the easiest way possible. Okay. So as we observe the universe, what we notice is that galaxies are moving further apart from each other. I'm going to draw some galaxies. Here's one. I can't draw very well. Here's another one. Here's one. Here's another. Let's just say this is us, and this is Andromeda. We're going towards each other. All the other galaxies outside of our local supergroup are moving away. Cool. And in fact, based on its distance away from us, a galaxy is moving away faster. Now, we usually call this universe expansion. If you accept that this expansion exists and has existed through time, there would have been some point at which all of that matter existed in a smaller region. Let's just say here, we're going to call this the cosmic A. And I'm going to put all of the stuff in there. Let's put everything in there. And then at some point, there begins an expansion away from this point. And people call that expansion the quote-unquote Big Bang, but there's a lot of misconceptions about what it is. The Big Bang is just the moment of the beginning of the expansion of the universe. All of our math and physics breaks down at this point, at the beginning, right? Whatever happened before that, if before that even means anything, I don't know. So it's just the start of the expansion, not something magical. We're just using it as a start point. Okay, we still got time. So this is the last thing I wanted to make sure that we understood really quickly. I'm just going to put this up because I forgot to write it on the last screen. The universe. Approximately 13.8 billion years old. Put that in your notes somewhere. Remind me to get back to it. Okay, so I really want to just show you this light year here. It reminds you that light year is the distance that light travels in 1 year's time. And I also want to make sure you get this number here. 9.46 times 10 to the 15th meters. I hardly ever write it in meters. I usually do 9.46 times 10 to the 12th kilometers. But this is actually in base units, so this is a better number to use. Either way, that's followed by a lot of zeros there. 946000000. Yeah, it's a lot. If you want to put that in miles, it's about 6 trillion miles. About 6 trillion miles. Right? It's a lot. So we got some big distances. And remember, the closest star to Earth, other than the Sun, is 4.2 light years away. 4.2, 4.3. So 4.2 times this number. Really far. So we've got some distances here, right? So if anyone says, hey, are there aliens? And you're like, maybe. They're like, well, why haven't we found any? I mean, please look how far away they would be if they even existed. That's far. In fact, look at the organization of the closest stars to us. Here's Earth. And like we said, about 4.2, 4.3 light years away, we've got Alpha Centauri. Well, it's the Alpha Centauri group, which consists of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. So there's about 4 stars in a 4 light year radius. Then we've got Bernard star, about 6 light years away. And then we got WISE 1049, and the other one whose name I can't remember, which are in about 3 light years away. So what it seems like, the density of the main portion of our galaxy is about 1 star per light year, which seems to be an average density. So not a lot of stars, but still some. All right, last question. Let's just say the star Betelgeuse, which is one of my favorite stars, it's 600 light years away. If it explodes tonight, which one of these 3 things is true? We'll know because it'll be brighter than tonight's moon. We'll know because we'll be hit with debris. Or we won't know for 600 years in the future. What do you think?
3.
I have 1 3. Anybody care to disagree? Well, I'll disagree just for the fun of it. I don't know which one to disagree on, so I'm just going to agree. You are correct, sir. We won't know for about the next 600 years because look how far away Betelgeuse is. 600 light years. That means that it's going to take light traveling from Betelgeuse 600 time physical years to travel that far. So if it explodes tonight, we have no idea. Now, of course, what I always hope is that it exploded 599 years ago, and I'm going to go out tomorrow and then get a treat. So just remember, things that happen require time to travel to your eyes. So you see things as they were when they occurred. You see things as they were when they occurred. So when you look in the distance, you're not really looking in the distance. You're looking right here, right? Only the light that reaches your eyes can you perceive. What you're really perceiving is the passing of time. It's weird, right? I'll let you all think about that over the weekend. Have a nice break. Check your assignments and see if you can access assignments. Your introduction assignment should be due Tuesday, if it works. So check it out. I'm going to try really hard to make it work. If it doesn't, then I'll try something else. But that's all I have for today, right? Stop recording.